In this video, we are going to begin to learn about how atoms within organic molecules arrange into molecular structures forming bonds by looking at how we calculate the formal charges on individual atoms. So let's go ahead and get started with this. For this exercise, you will need a periodic table, which you can download. Any periodic table that would arise from a Google search will be sufficient for this. As well, if you are taking my class, I have posted a copy of the periodic table for you that will look just like the one that I'm about to show here. On this periodic table, we can apply the information to determine the formal charge on any individual atom within an organic molecule by applying the following formula. So this is going to be the formal charge formula, and this will allow us to calculate the formal charge on any individual atom within an organic molecule. So Fc is formal charge, so calculate formal charge on any individual atom. So if we're trying to determine the formal charge on a carbon atom, for example, we could apply this formula. The net charge on a molecule as a whole would be equal to the sum of the formal charges on all of the individual atoms within that particular molecule. So we could apply this formula to calculate the formal charge on each individual atom within a molecule, and then sum up all of those individual formal charges to get the total net charge on the molecule as a whole. So our formal charge formula for calculating the formal charge on any individual atom of our choice is going to be that the formal charge on an atom is equal to the column that that particular atom appears in within the periodic table. So we're going to do column of the periodic table. That's why I've displayed the periodic table here. Minus the number of covalent bonds that go to that particular atom. And if we have a double bond, such as is the case with an alkene, that would count as 2 covalent bonds. And then we also subtract from that the number of electrons that are in lone pairs. So number of electrons in lone pairs, which I'll abbreviate as LPS. And the counting of this always gets a little bit tricky. We could also synonymously think of this as the number of unbonded electrons. In other words, the number of electrons that are not shown as lines representing covalent bonds, but instead are shown as dots, indicating that those are unbonded electrons, and we count those individually here. So every single unbonded electron counts toward this number here. So don't get confused and think, oh, lone pair counts as 1. Instead, what is really the case is that a lone pair of 2 electrons would count as 2 in this part of the equation. So for example, as we have the periodic table up here prominently, let's look at a carbon atom that is part of an alkene group. So we're going to draw this 2-carbon alkene, ethene. And this is a cool molecule because this is a trigger of ripening of fruit. Particularly bananas are sometimes treated with this synthetic chemical to induce them to ripen faster during storage so that they're ready to sell faster. So this particular molecule, if we are to calculate the formal charge on the individual carbon atoms here, that could be something that we would be tasked with. We'll take a look at the carbon atom here that I've highlighted in gray, and I'm going to color code my work here as well. So we're going to do the formal charge on that carbon. And calculating that, the formal charge on our carbon being equal to the column of the periodic table that the carbon atom resides in. So we find carbon on our periodic table here. I'm going to highlight that in yellow over here. Now the way that we count what column that is in for purposes of finding our formal charge is number 1 is this column here to the far left that has hydrogen. Number 2 is here, so it's following these numbers right here in Roman numerals 2. And then we come over to here for number 3. The transition elements, as they're called, are here in the middle. Those behave oddly, and we're not going to be getting into those in the field of organic chemistry, so I'm ignoring those for purposes of our exercise. Column 4 here, 5, 6, 7, and 8. So that is what we're referring to when we talk about the column of the periodic table. We're referring to the numbers that I have shown in green there. So when we're calculating the formal charge on our carbon atom that we have highlighted here in gray, formal charge on that carbon is going to be equal to the column of the periodic table that carbon appears in. That's column number 4 over here, minus the number of covalent bonds that go to that particular carbon atom. So counting the number of covalent bonds there, that's the number of lines going from this particular carbon. We have 1, 2, 3, 4, because we count both of those lines of the double covalent bond here. So 1, 2, 3, 4 covalent bonds. So I'll subtract 4 there. And the carbon atom here in this structure has no lone pair electrons, and so number of electrons in lone pairs, we're going to subtract 0 there. So the formal charge on carbon in this case is going to be 4 minus 4, which equals 0. And that comes as no surprise if we think about what creates a relatively stable molecule. Stable molecules typically have atoms that have no formal charges. That is what is going to help to confer stability on them. And so in this relatively stable alkene molecule, we have a 0 formal charge on the carbon, as is expected. The same formal charge will be found on the carbon here on the right that I've highlighted in yellow, because that particular carbon has the same motif of 4 covalent bonds coming from it. And the fact that 4 covalent bonds on carbon enables carbon to have a formal charge of 0 is one of the reasons why carbon prefers that motif. The other is that 4 covalent bonds allows it to have a complete octet. So allowing the atom to have a complete octet and no formal charge is beautiful in terms of creating an atom that is as stabilized as possible. So let's go ahead and do some additional examples of calculating formal charges using this equation that we have just posted here. So we'll continue to apply this towards some additional problems. So what I'm going to do is go ahead and shrink this down a bit so that we still have that periodic table up in the upper corner and we still have our formula there. And now we're going to work through an additional practice problem or two here where we're going to be tasked with, for example, calculate the formal charge on all atoms in this particular structure. And we're drawing this as what we refer to as a Lewis structure. A Lewis structure is one that shows all of the bonds, all of the lone pair electrons, and all of the atoms within the structure explicitly. We will get into some abbreviated ways of drawing organic molecules a little bit later on in the course. So I'll go ahead and draw in here, and I'm going to actually add a little addendum to what we've posed as our question here. Rather than doing it for all atoms, let's do it for all non-hydrogen atoms. We don't want to get too carried away here with our example problem for now. So calculating the formal charge on all non-hydrogen atoms, let's go ahead and do that. I'm going to highlight my non-hydrogen atoms here that we have to deal with. Carbon, carbon, nitrogen, and oxygen are the atoms that we will be working with. So I'm going to begin with the formal charge on the nitrogen atom here. Formal charge on the nitrogen, that atom right there, going to be calculated as following our equation here in the upper left-hand corner, which is definitely worth your time to solidify in your mind so that you will have this ready to go when you need it. Column of the periodic table that we find nitrogen in, looking at our periodic table here, nitrogen is going to be in the 5th column of the periodic table, that number 5 there in green. So I'm going to go ahead and fill in 5 here as the column of the periodic table that we find nitrogen in. And then number of covalent bonds going to nitrogen is equal to 3. So there's 1, 2, 3. So I'm going to go ahead and fill that in as 3 here. And then number of electrons in lone pairs. So we have a lone pair right here, and remember that counts as 2. We count each dot by itself. Don't forget that. That's a common mistake that people make when getting started with this. So it's going to be 2 electrons that are in lone pairs, or unbonded electrons as you might call it. So tallying this up, 5 minus 3 minus 2 equals 0. And as a consequence of the fact that nitrogen when it's in this motif of 3 covalent bonds, 1 lone pair of electrons, and having a complete octet of 8 electrons surrounding it in total. That is going to make for a very stable motif of nitrogen. So it's no coincidence that we see nitrogen appearing very commonly in nature with 3 covalent bonds and 1 set of lone pair electrons, because that's going to enable nitrogen to have that magic combination of having a complete octet of electrons and having no formal charge on it. So let's carry on to the next atom here. Let's go ahead and do our oxygen atom. Calculating the formal charge on the oxygen. Oxygen, we will find if we take a close look at our periodic table here, oxygen is highlighted in blue there in the 6th column of the periodic table right here. So I'm going to fill in the number 6 to represent the column of the periodic table in our equation for formal charge. Number of covalent bonds coming from oxygen. Remember that if we have a double bond, it counts twice. If we had a triple bond there, we count 3 times. So 1, 2 covalent bonds. So I'm going to fill in 6 for the column of the periodic table minus 2 covalent bonds minus number of electrons in lone pairs. We have 1, 2, 3, 4 electrons in lone pairs. So I'm going to fill in minus 4 there. So the formal charge on the oxygen atom, that is an O there for oxygen, not a 0. So the formal charge on the oxygen is equal to 6 minus 2 minus 4. Adding that up gives us a formal charge of 0. And we will notice universally that oxygen has a strong tendency to have 2 sets of lone pair electrons and 2 pi bonds coming from it, because of the fact that that is going to enable the oxygen to have that magic combination of a formal charge on the atom of 0 and having a complete octet. Because if we count up the number of electrons around this oxygen, the covalent bonds give us 2, 4 electrons in total, plus 2 and 2 from the lone pairs give us a total of 8 electrons, filling the octet for that oxygen. And then we can carry on and do this same sort of calculation for our carbon atom. Let's go ahead and do that for this carbon here first. So our formal charge on the carbon atom, that's the carbon that is directly bonded to oxygen and nitrogen, the one that I've highlighted in green here in our structure. Formal charge on that carbon. Carbon is in the 4th column of the periodic table, as we saw before in the periodic table. So we'll fill in number 4 here. Minus the number of covalent bonds to that carbon atom is 2 bonds to the oxygen, 1 bond to the carbon, and 1 line or 1 bond to the nitrogen gives us 4 covalent bonds. So we 4 minus 4, and then we see no lone pair electrons on that carbon, so that'd be 0. So 4 minus 0 gives us 0 as the net formal charge on that carbon. And it's no coincidence, anytime you see a carbon that has 4 covalent bonds and no lone pairs, that carbon is going to have a complete octet, and it's going to have no formal charge. So the same calculation would apply toward this carbon atom right here, because this carbon also has a total of 4 covalent bonds and no lone pair electrons. Now let's go ahead and clean off the slate and do one more example problem to make sure that we have got this concept down. I'm going to erase here. Okay, so in this, let's do this example where we're going to calculate the formal charge Fc on the nitrogen atom in the following molecule. So I'm going to go ahead and draw out the Lewis structure of this, which shows all of the bonds, all of the lone pairs, and we're going to try to calculate the formal charge that would be present on the nitrogen atom in this particular molecule. So taking a look at and finding our nitrogen atom, which is what we're tasked with determining the formal charge on. We have our nitrogen right there. Now coming in to calculate the formal charge on that nitrogen, using our formal charge equation that we've kept up here in the upper left-hand corner of our screen. Formal charge on the nitrogen is equal to the column of the periodic table that nitrogen is in. That's the 5th column of the periodic table, as we saw up here in red. We're going to subtract the number of covalent bonds. That's 4 covalent bonds because we have 4 lines coming from nitrogen representing our covalent bonds. And then we have no lone pair electrons that we're seeing, so we're going to put in a 0 there. So the formal charge on the nitrogen atom would be 5 minus 4, which equals plus 1. So the way that this would be shown within the structure is if we want to indicate that that nitrogen has a formal charge on it, we could apply that by showing superscript positive there. And indeed, if you're drawing a structure from scratch and an atom has a formal charge, then you are to put that formal charge on the atom. It's a requirement. So we start off this structure and we've drawn the skeleton out. And then once we calculate the formal charge on the nitrogen atom, we need to put that information into the structure for the structure to be finalized. If an atom has no formal charge on it, then we don't need to include that information. But here it had a positive charge, so we put that in. In the previous structures we were working with earlier examples, all of the atoms had 0 charge, so we didn't have to fill in any additional information there. But here we have a positive charge, so we need to fill that in. You will notice here that the nitrogen does have a complete octet of electrons, so it's not a completely horrible, unstable situation for the nitrogen to be in, but the nitrogen in this case is not as stabilized as it would be if the nitrogen had an octet and had no formal charge. The formal charge inevitably, to some extent, destabilizes the molecule. So based on what we have seen here, there are some general trends that we observe when we are thinking about the typical motifs of how electrons arrange around particular atoms. And it's worth noting these motifs that we see, because these are common motifs that accomplish filling the octet and giving a stable formal charge of 0. And we will most typically see these motifs when we are drawing organic molecules that are stable and have practical applications in nutrition, medicine, and other fields. So when we are looking at a carbon atom, the motif that we are going to see for carbon is that generally the number of covalent bonds that the carbon atom will have surrounding it is going to be equal to 4, as we saw with alkanes, alkenes, and alkynes, and other ways that we've seen carbons bonding to other atoms so far. And then the typical number of lone pairs that we will see on carbon atoms is generally going to be 0. That is what's going to allow us to create a carbon atom that's stabilized, and that's going to be what we see within the structures that we'll be working with in this particular class. Oxygen atoms, on the other hand, in order to fill their octet and have a 0 formal charge, to accomplish that are going to have 2 covalent bonds and 2 sets of lone pair electrons. So these are number of lone pair electron sets. So 2 sets of lone pair electrons would be 4 electrons within a lone pairs in total. So an example of this would be if we had an oxygen atom that's directly connected to 2 carbons, that oxygen would have 2 sets of lone pair electrons to allow it to have a complete octet and have no formal charge. So I've highlighted in pink here the 2 covalent bonds that oxygen prefers to have, and then 2 sets of lone pair electrons. So this would be a very common way that we would see oxygen appear, is having single bonds to 2 different other atoms, such as carbons, or they could be other atoms here, as well as 2 sets of lone pair electrons. Another common way that we see oxygen appear, as we'll see oxygen as part of a double bond that leads to a carbon atom, and that oxygen also, in this case, will fit the rules for being relatively stable because that oxygen has 2 covalent bonds still. It's just part of a double bond rather than 2 single bonds. And that carbon, or oxygen I should say, has 2 sets of lone pair electrons. So this is a couple of common motifs that you'll see for oxygen, and it's worth putting these into your memory bank as common motifs so that you don't have to calculate the formal charge on the oxygen every time you see it in this type of structure. Instead, you can look at it and quickly realize, okay, oxygen has 2 covalent bonds and 2 sets of lone pairs, therefore it has a formal charge of 0. And that way you don't have to go through and do this calculation that can be a time sink every single time. You always have the calculation available to you, but you don't necessarily want to spend your time, your valuable time, working on those calculations for every single atom. So that's why we're looking at some of these common motifs. So if you see the motif, you will know that the formal charge is going to be 0 on that particular atom, and that the octet will be filled for that atom. In the case of nitrogen, nitrogen's preference is 3 covalent bonds and 1 set of lone pair electrons. And the typical way that we will see that for purposes of this class is we'll see a nitrogen has 3 covalent bonds going to other atoms. I'm just going to draw those lines going to nowhere, indicating they go off to whatever else we want, and then 1 set of lone pair electrons. So we have our lone pair electrons, 1 set, and then 3 covalent bonds, and those 3 covalent bonds are in yellow, 1, 2, 3. And then finally, we also commonly see halogen atoms within organic molecules. And so for halogens, halogens are atoms from the next to the last column of the periodic table. So that is everything right here. Fluorine, chlorine, bromine, and iodine are what we refer to as our halogens. And halogens are going to have a preference for having 1 covalent bond and 3 sets of lone pair electrons in order to fill their octet and have no formal charge. So example of that would be if we had a carbon bonded to a bromine. That bromine is generally going to have 3 sets of lone pair electrons. So we have our 3 sets of lone pair electrons here. I'm going to highlight in green: 1 set, 2 set, 3 set. That's our number of sets of lone pair electrons, and then 1 covalent bond there. That's going to give a complete octet on bromine, and it's going to allow bromine to have no formal charge. So if you did the formal charge calculation using the equation up here for our bromine atom, you should find, if you've done it correctly, that the bromine will have a formal charge of 0. And it's worth doing that calculation as a way of finishing up this video.